Good morning everyone. Today we are going to see a lecture on neural networks based robot control. The outline of this lecture will be as follows. First we have the introduction to neural networks and the biological inspiration towards ANN, artificial neural network. Then we are going to see perceptron, then multi-layer perceptron. Then we will be seeing multi-layered neural network, its architecture, and then we will be seeing the principle of gradient descent. Next we move on to back propagation algorithm, which is an important algorithm towards neural network based robot control. Then we will be seeing inverse kinematic control using neural networks with an experimental demo, and then we finally conclude our lecture today. Thank you. So, we will start with the introduction part. First we start with the biological neural networks. The important thing is nerve cells. Two types of nerve cells are there, which are glial cells and neurons. The glial cells will not take part in transmitting or receiving messages, rather it will protect the neurons, and each yellow structure represents a neuron here in this schematic. The neuron is the functional unit of the nervous system. Approximately there are 100 billion neurons in the human brain. Now coming to the neuron structure, the pyramidal cell, which is a common neuron given here. So, here each neuron has three parts: dendrites, cell body and axon. Dendrites receive information from another cell and pass it to the cell body, this message what it has received. The cell body contains the nucleus, mitochondria and other organelles typical of eukaryotic cells. The axon conducts messages away from the cell body. Let us talk about synapse now. The junction between a nerve cell and another cell is called synapse. So, the messages travel within this neuron are basically electrical active or action potentials. Messages travel within neurons happen through action potentials, which are electrical action potentials. The space between the two cells is known as the synaptic cleft. In order to cross the synaptic cleft, it is required to have the actions of these neurotransmitters, which are stored in small synaptic vesicles clustered at the tip of the axon. Now, let us see the basic functions of our biological nervous system. They receive sensory input from the external as well as internal environments, and they integrate the received input, and finally they respond to the stimuli by producing a response or output. So, the biological inspiration is that the living organisms react adaptively to the changes in their external as well as internal environment, and they use their nervous system to perform these behaviors. Now, the artificial neural network must replicate this behavior. Thus, artificial neural network is basically an approximate model or simulation of the nervous system that should be able to produce similar responses and behaviors in artificial systems. Let us talk about the fundamental unit of an artificial neural network, which is a neuron. A single neuron is called a perceptron. So, it has a structure like this. It has a summer. The output of the summer goes to a function called transfer function, and then we get an output. The summer receives two inputs. One is the given input, scalar input multiplied by the scalar weight will become one part of the input to the summer, and the another term of the summer is the input 1 multiplied by the bias. That is why 1 into b. So, the input that the summer receives is two terms, basically the first term Wx plus b, and that input goes as input to the transfer function. The transfer function has this input n, which is Wx plus b as its input argument. Accordingly, we get the output A based on the transfer function. Likewise, for the multi input neuron, we have the neuron structure with so many inputs. So many inputs connected to the summer through a weight vector. So, the input to this summer is basically W vector, weight vector multiplied by the input vector, plus B, which is the bias, the input multiplied by the bias. So, that acts as the input to the transfer function, which is f. Thus, A is a function of Wx plus B, where W is a vector called weight vector, x is the vector called input vector, and B is the bias input. Now, let us see about the activation function or transfer function. In general, they take these forms. One is a linear transfer function, which means the output is the input, which is phi of z equal to the given input z, and the logistic activation function is sigmoidal activation function, which takes the range 0 to 1, which has the mathematical expression 1 by 1 plus e power input minus input. Similarly, we have another form of the sigmoidal function, which is hyperbolic tangent function, which is given by phi of z equal to e power z minus e power minus z upon e power z plus e power minus z, which takes this output range varying from minus 1 to plus 1. The profiles of the linear activation function and the logistic sigmoidal function and the tan hyperbolic function, all these three are given here. As I said, linear activation function, the response is linear. Logistic sigmoidal function will have the sigmoidal curve varies from 0 to 1. Tan hyperbolic activation function will have the curve which is varying from minus 1 to plus 1 as its response. And because the linear function produces output based on the input, which is linear in relationship, it is limited to getting applied to complex neural networks, whereas the sigmoidal activation function will be applicable in complex neural networks, where its range is between 0 and 1. Similarly, the tan hyperbolic one, which is given by the expression e power z minus e power minus z upon e power z plus e power minus z, has its response varying between minus 1 and plus 1. Now, coming to the fundamental application of artificial neural network is towards classification and regression. Classification predicts categorical classes precisely coming under the discrete domain. The basket having different colored balls or apples will be segregated based on the colors of the apples. So, they are coming under 3 classes, let us say 4 classes. So, each class 1, 2, 3, 4 becomes discrete quantity. And regression, it models continuous valued functions. Thus, classification is to identify which class and regression is to estimate continuous quantity. Thus, classification is finding function that maps input into classes. Thus, class equal to function of input. Given a input x, it belongs to which class is the output of the classification. For example, if you take an hand exoskeleton to move the fingers towards grasping and releasing. So, grasping is one class, releasing is another class towards the on off controller. Okay, based on the input subject intention through the brain signal or through the muscle signal, the exoskeleton will help the elderly human beings to grasp objects or to release that. That is the output of classification through neural networks application. And regression is to find a function that maps input into values. Thus, value is basically a function of the given input x. And here the robotic example is inverse kinematics control. Given a desired position to reach, you get the corresponding joint angle vector of the robotic system to reach that position in the Cartesian space. And thus, we have a continuous mapping between the Cartesian space and the joint space. Next, let us see the architecture of the fundamental neural network. Let us take an L layered neural network. You can see the input layer where the inputs are x1, x2, x3 up to xm, which means m layered inputs. And we have the hidden layers numbering n minus 1 hidden layers and 1 output layers. The output layer it is n. Thus, the hidden layers are L1, L2, L3 and it goes on, whereas the output layer is the last layer which is L suffix capital N. Thus, it is an L layered neural architecture. So, we can see here the L layered architecture consists of an input layer of source nodes, L minus 1 hidden layers and an output layer which is the Lth layer. If it is a 3 layered network, the third layer is the output layer and 2 hidden layers are there and 1 input layer. The synopsis of these notations used to represent an multi-layer neural network with L layers is given as, let x be the m cross 1 input vector and y be the output. We can say instead of y we can say it is O being the output, small o, and Lk where k varies from 1 to L is the index for representing a neuron in the kth layer, and WLK Lk minus 1 represents the synaptic weights connecting the Lkth neuron of the kth layer to the Lk minus 1th neuron of the k minus 1th layer, which means that W L1 L0 implies the synaptic weights that connecting the L1 neurons to L0 neurons. Now, let us see the principle of gradient descent. Here we need to calculate the derivative or the gradient of the error with respect to the weights and then change the weights by a small increment in the opposite direction of the gradient. Thus, the rate, thus the rule here is W nu equal to W volt minus eta dou E by dou W. Now, how this one came, which is basically W nu is equal to W old plus delta W, change in W. So, in this profile between the error function and the weight vector, we need to find the optimal weight vector where the error function is minimized. So, we have here the negative slope and the positive slope in this direction. So, when we are here, we have to increment delta W positively. When we are here in the W, let us say initial W is here, then we have to go towards this point for this optimal value, and hence delta W here is decremented. So, for delta W we take this expression minus eta into dou E by dou W, where dou E by dou W is the slope. So, here if you want to do, delta W must be positive when we start from here to reach the optimal value, where it corresponds to the minimum error function or the cost function. So, here it must be positive, whereas the slope is negative slope. So, delta W being minus eta dou E by dou W becomes minus eta into minus value because of negative slope. So, it becomes positive. Thus, we start from here leads towards positive increment of delta W. Similarly, when we start from this point, delta W is decremented towards the optimal value of W. So, for both cases this rule obeys, where eta is the learning rate. It varies from 0 to 1 value for eta learning rate. Higher the learning rate, faster is the convergence. Smaller the learning rate, convergence is slow. So, here the cost function is defined as summation over pattern 1 to n patterns, input output patterns, EP, where EP is given by half into output of that pattern in a designed manner, desired output pattern minus current output pattern whole square, where OP and OPD denote the pth actual and desired patterns, and eta is the learning rate, as I told you, that varies from 0 to 1. Next, we see the back propagation algorithm. So, the objective is to adjust the weights of the network so as to minimize the cost function, which will train the network for mapping of the required function. For function approximation, we need to train the network, which means that adaptation of the network parameters towards the given input, so that the network can be able to approximate any given input function. So, through back propagation algorithm, we are going to see how the network parameters are updated, and the parameters of the network getting updated leads to a term called training of the network or network learning. The back propagation algorithm uses the principle of gradient descent to train the network parameters. Let us define the output, input and weight parameters associated with the network. X being the m cross n input vector and O being the n cross 1 output vector, and ik minus 1 represents the weight connecting ikth neuron of the kth layer and ik minus 1th layer neuron of the k minus 1th layer, and hi response, which is nothing but the response of the ith neuron in layer 1. Let us see here. Let us consider, to derive this back propagation algorithm, a 3 layered network. X1 to xm is the input layer, where the sources are x1 to xm, which means x is an m cross 1 input vector, and we have 3 layers L1, L2 and L3, where L1 and L2 are the hidden layers and L3 is the last layer called output layer. So, this network has 1 input layer, 2 hidden layers and 1 output layer, and you can see here the weights connecting the first hidden layer L1 to the input layer L0 is represented by W L1 L0. This is the nomenclature that I give to the weight vector connecting first hidden layer to the input layer. Likewise, for the second hidden layer to the first hidden layer, the weight vector is given by W L2 L1, and W L3 L2 is the weight vector connecting the output layer L3 to the second hidden layer L2. And you can see the outputs of the first hidden layer is given by H1, H2, H3 up to Hn1, where there are n1 number of neurons in the first hidden layer. Likewise, the output of the second hidden layer is also given by H1, H2 up to Hn2, because there are n2 numbers of hidden neurons in layer 2. So, what is observed here is the neurons output is given by H1, H2 like that, which are precisely the hidden layer neurons output, whereas the output of the neurons in the layer 3 represented by H1, H2, H3, basically they are the outputs of any neurons. Because the third layer is the output layer, H1 is represented as O1, H2 as O2 and H3 as O3 and Hn3 as O5. Accordingly, we have the output of the neurons of the output layer is represented by O2, O1, O3 up to On3. Next, we have 2 phases in training the neural network in back propagation based algorithm. The first one is forward phase, which means we are getting the response or output of the neurons present in the hidden layer as well as the output layer based on the weight vectors as per the input given. Given an input, getting the response is called forward phase. Here the input to the L1th neuron of the first hidden layer is SL1, which is given by the summation over L0 to 1 to n W L1 L0 multiplied by the input vector, and the output of the L1th neuron of the first hidden layer is HL1, which is given by transfer function of the input SL1. Since we use the transfer function being sigmoidal transfer function, which takes the form 1 by 1 plus e power minus input, where the input is SL1, that is why it is minus SL1. Likewise, the input to the L second neuron of the second hidden layer is SL2, which is given by summation over L1 to L1 equal to 1 to N1 W L2 L1 HL1, and the output of the L2 neuron of the second hidden layer is HL2, which is transfer function of SL2, which is the input, that is given by the sigmoidal transfer function expression 1 by 1 plus e power minus input, which is SL2. Next, the forward phase continues. The input to the third layer, which is the output layer, that is SL3, which is given by summation L2 equal to this N2 1 to N2 W L3 L2 HL2, and the output is given by of the output layer is O L3, L3 is the output layer and O is the output from that network. So, O L3 equal to transfer function of SL3 input, thus 1 by 1 plus e power minus SL3. Now, let us see the back propagation of error. This is the starting phase of the backward phase, forward phase and the backward phase. The instantaneous cost to function in error is given by E of t equal to summation L3 equal to 1 to N3 EL3 of t, which is given by half into summation L3 equal to 1 to N3 expression for EL3 we are writing, which is output desired minus actual output whole square. So, the weight update starts here based on the backward propagation of the error. So, the update of the weights connecting the output to the hidden layer is the first step, because from the back side the first layer that we are going to face is the second hidden layer and the output layer. So, the weights connecting the second hidden layer and the output layer is to be first updated. So, WL3 L2 of t plus 1 equal to WL2 L3 of t plus delta W L2 L3, where delta W L2 L3 is given by minus eta dou E by dou W L3 L2 of t, where this term, the second term dou E by dou W L3 L2 is given by again the summation over L3 equal to 1 to N3 dou E L3 by the output partial derivative into the output partial derivative upon this one, where the chain rule plays a vital role. So, for the sigmoidal activation function, the transfer function of the given input is given by 1 plus e power minus S Lx Lk, which is the input to the activation function. Thus, the partial derivative of this with respect to its input is given by an expression, this is e power minus SLk upon 1 by 1 plus e power minus SLk whole square. Thus, leads to psi minus psi square, which is nothing but the function into 1 minus the function. Thus, dou psi of this upon dou input is equal to 1 minus psi into psi. So, from the cost function of the error, we can write dou E L3 of t upon dou O L3 is given by minus 1 by 2 into 2 times of O L3 d minus O L3 actual, since error is half into desired OL3 minus actual OL3 whole square. That is why this has become your partial derivative of EL3 with respect to OL3. Then the second term dou OL3 upon dou WL3 L2 is given by dou OL3 upon dou SL3 into dou SL3 upon dou WL3 L2 because of this cross chain rule. Thus, this leads to output into 1 minus output multiplied by the hidden layer 2's output. This is obtained because of the sigmoidal activation function's derivative with respect to its input. Then combining equations 3 and 4, the previous equation 2 becomes dou E upon dou WL3 L2 of t becomes minus OD minus OL into OL3 into 1 minus OL3 into the output of hidden layer 2. So, this portion into this portion with the minus sign, that is what combinedly here. Now, we can see thus the weight update law WL3 L2 of t plus 1 becomes WL3 L2 of t plus this term, because minus eta dou E by dou W. So, minus minus plus, so it is this expression. Okay, so, this expression completely equation 6 can be written in equation 7, where we have delta L3 into eta HL2, where delta L3 is given by OL3 desired minus OL3 actual into OL3 into 1 minus OL3. Likewise, we can see the update of the weights connecting between the two hidden layers, that is layer L2 and layer L1. Thus, the weight update law becomes WL2 L1 of t plus 1 equal to WL2 L1 of t minus eta dou E by dou WL2 L1 of t, where dou E upon this term dou WL2 L1 of t is given by this expression, where we need to expand these two expressions, that is dou E L3 of t upon dou O L3 and dou O L3 upon dou W L2 L1. Let us take this expression first. Dou O L3 with respect to dou WL2 L1 is given by dou OL3 upon the output from the L2 into output from the L2 upon dou WL2 L1. So, this term further expanded into dou OL3 upon dou SL3, which is input to the output layer SL3 into chain rule, this and this dou SL3 upon the output from L2, that leads to this. Okay, so, this one is OL3 into 1 minus OL3, whereas input to the third layer with respect to output from the second layer gives you WL3 L2. Okay, so, we know that OL3 is given by this expression because of the sigmoidal activation function, and SL3 is given by this expression, and thus SL3 partial derivative with respect to HL2 will give you this term, that is what it is here. Now, the second term of equation 11 can be written as dou HL2 upon dou WL2 L1 being dou HL2 upon the input to second hidden layer, that is SL2 partial derivative. With the chain rule we can have with respect to dou WL2 L1, that leads to this term, that is HL2 into 1 minus HL2 into HL1. Now, combining equation 13, 12 and 3, equation 10 can be written as dou E upon dou WL2 L1 becomes finally minus HL2 into 1 minus HL2 into HL1 summation L3 equal to 1 to N3 dou L3, that is delta L3 WL3 L2, which is 14th equation. Thus, the weight update law, that is for the second weight connecting L2 and L1 layers, become WL2 L1 of t plus 1 equal to WL2 L1 of t plus eta delta L2 into HL1, where delta L2 is given in terms of delta L3 as HL2 into 1 minus HL2 multiplied by the summation L3 equal to 1 to N3 delta L3 WL2 L3, which is equation 16. Now, finally, we can go for the update of the weight vector connecting the first hidden layer to the input layer, that is L1 and L0. Thus, WL1 L0 of t plus 1 equal to WL1 L0 of t minus eta dou E upon dou WL2 L0 of t. In the same way, when we continue this, we end up the weight update rule for this weight vector, which is connecting L1 and L0 rule becomes WL1 L0 of t plus 1 equal to WL1 L0 of t plus eta dou L1 x L0, where dou L1 that is delta L1 is given in terms of delta L2 as HL1 into 1 minus HL1 multiplied by summation L2 equal to 1 to N2 delta L2 WL to L1, which is equation 16. Now, let us see generalized delta rule can be obtained in terms of this example. Let us consider a 4 layered network where delta L4 represents desired output minus actual output into 1 minus actual output. Thus, W L4 L3 of t plus 1 equal to L4 L3 plus eta into del L4 HL3, where HL3 is the output from the third layer L3. Likewise, we can go for the third layer update rule, which is WL3 L2 in terms of delta L4. Likewise, the second layer in terms of delta L2, where delta L2 is written in terms of delta L3, whereas for the first layer we can say, which is connecting the weights between layer L1 and L0, input layer and the first hidden layer. Thus, it is given by WL1 L0 of t plus 1 equal to WL1 L0 of t plus eta del L1 into the input to this layer. And thus, delta L1 is given in terms of delta L2 as HL1, which is the output of hidden layer 1 into 1 minus HL1 multiplied by the summation L2 equal to 1 to N2 delta L2 WL to L1. Now, let us come to the application of neural networks towards inverse kinematic control utilizing the back propagation algorithm that we have seen before. So, here it is basically meant for inverse kinematic control problem, where a robotic system is here. In the Cartesian space, we have x actual, y actual, it has to go to x desired, y desired point in space. So, given this space, we need to move this robotic system to reach here by providing the joint angular vector containing theta 1 and theta 2. So, this is now theta 1 updated and theta 2 updated. So, to solve this inverse kinematic control problem, we go by using this multi-layer neural network with the BPN algorithm. Given the desired position in space xd, yd and say zd, 3D Cartesian space position to the network weights are updated, which connects between the output layer and the hidden layer and the hidden layer and the input layer and so on. So, the network given the input with the associated weights, the network is updated, the network with the network parameters, we get an output. That output of the network is considered as the joint angular vector of the robotic system, and that joint angular vector has been given as input to the forward kinematic model of the system, robotic system, and hence we get an actual value of the robotic tip for the desired tip position, and the error between the desired and the actual tip position obtained from the forward kinematics through the input by the network output, we have the error function that has been back propagated to update the weight parameters connecting hidden to output layer and input to hidden layer. These two weights are updated, and then with the updated weight parameter again another input vector representing the different Cartesian position for the robotic system is given, and then the process is continued till the error is minimized under a tolerable value. That is how this training of this network happens. This procedure is almost a semi supervised or semi unsupervised learning, this procedure to get the results, and with this we can able to track the given desired trajectory precisely. And here is the pseudo code for this inverse kinematic control based on neural networks. Given the desired value, continue the loop with condition for stopping the loop, that if the error is less than a tolerant value, stop the loop or continue with the loop. The network output for the given input is basically joint angle that has been given to the forward kinematic model in order to obtain the actual network output, because we need to compare the Cartesian desired position with the Cartesian actual position of the robotic system, and the error is back propagated, which is given by this expression, which is back propagated in order to update the network parameters, and with the updated network parameters we give another new desired Cartesian position for the robotic system to reach, and this process continues until the error is less than a tolerable value. Now, this is the demo that we have done this type of semi unsupervised learning technique towards a regression problem to solve this inverse kinematic control of a 5 degrees of freedom follower robot towards minimal invasive surgery. The demo is given here. Where we have controlled the follower robotic system by giving a master command through the haptic device, so that the follower robot is here, which is 5 degrees of freedom, has 5 links, has to follow the given tip trajectory, and that given tip trajectory has been tracked by providing the joint angular value obtained from the neural network, and we could achieve that through this neural network simple approach. And here, coming to the conclusion point of this lecture, we have seen first introduction to neural networks, then we have seen back propagation neural network algorithm, then we have seen generalized delta rule, and then we have applied neural networks towards inverse kinematic control of a robot. Thank you so much.